Hello everyone, welcome back to another video. Today we'll be talking about transformers, which is the architecture that powers a lot of the modern AI we have today. We'll explore the core concepts that enable transformers to understand and generate human-like text. The goal today is to provide an understanding of these complex models, focusing on the key components that make them work. When we look at it really closely, a language model just aims to predict the next word in a sentence. You can think of it like Gmail suggesting the next word as you type. That's a language model in action. Then you have other models like GPT, which takes this a step further. They predict the next word and then they use that word to predict the word after that, generating a complete answer. GPT stands for Generative Pre-trained Transformer. It is also called a large language model because it contains billions of parameters, which makes it more capable and powerful than your normal basic average AI. When you ask a question to ChatGPT, it predicts the next word based on the context, and then it continues by predicting subsequent words based on the original question, allowing it to produce full and coherent answers. Again, when we look at it, machine learning models don't understand text directly. It's more like they understand the numbers. So, a way we can translate these words into numbers is to represent them numerically using word embeddings. One way to achieve this is to represent the word as a vector, in which a vector is a list of numbers derived by asking a series of questions. For example, for the word king, you might ask, does this person have authority? And the answer would be most of the time yes. Do they have a tail? Probably not. Are they rich? Probably are. And what is their gender? And since we're talking about king, we're gonna be using one, as -1 would represent a female. By representing words as vectors, we can kind of perform math with them. We can see this like king minus man plus woman results in a vector that would be similar to what a queen would be. Real world models, like Google's Word2Vec, can use hundreds of dimensions. But models like ChatGPT, on the other hand, can go up to 12 to 13,000. With static embeddings, each word has a fixed representation regardless of the context. Word2Vec and Glove are examples of models that can generate static embeddings. However, the meaning of a word can change based on the sentence it's used in. For example, the word track has different meanings in the train will run on a track versus help me track my package. Contextual embeddings, on the other hand, address this limitation by allowing the surrounding words to influence the embedding of a word, thereby capturing its specific meaning in that context. The static embedding for the word dish can be modified based on whether it's a rice dish, an Indian dish, or a sweet Indian rice dish. To generate contextual embeddings, you need to take the original static embedding and have other words influence the static embedding. Before words can be turned into embeddings, the input text needs to be broken down into smaller units called tokens. Tokens are like words, but they can also be pieces of words or punctuation. For instance, playing might be tokenized as play and ink. Models have a predefined vocabulary. For example, GPT-3 has a vocabulary size of around 50,000. A special token is added to the beginning of the sentence, and a separator token is added in between two sentences. Each token is then assigned an ID, which is its index in the vocabulary. For example, if the word made is at the position 2532 in the vocabulary, then its token ID would be 2532. Positional embedding is where the model will add a small vector in each of the embeddings. Positional embeddings provide the model with information about the order of words in a sentence, since transformers process the entire input sequence in parallel. The location of the word matters because if you put the word made before I, it will change the meaning of the sentence. A lot of the computation in transformers looks like matrix vector multiplication. The model parameters are referred to as weights. Usually, after computing the results of these matrix multiplications, we end up with a value that is not necessarily between 1 and -1. So we can input it into a softmax function, which pretty much converts raw output scores, known as logits, into probabilities by taking the exponential of each function, normalizing these values by dividing them by the sum of all the exponentials, which is pretty much the equation we see on the bottom. And what that does, to put it short, it generalizes all the matrix numbers and puts it in a way where we can add it all up to 1. Or to put it short again, the softmax function turns an arbitrary list of numbers into a valid probability distribution. If you want a sequence of numbers to act as a probability distribution, then each value has to be between 0 and 1, and you need all of them to add up to 1. A transformer consists of two main parts, which is the encoder and the decoder. The encoder takes an input, something like a sentence, and converts it into a structured representation in the form of a set of numerical vectors that captures meaning. It processes the entire input at once and extracts contextual information. For example, if we input the sentence, "The cat sat on the mat, enjoying the warm afternoon sun," the encoder will transform this sentence into a numerical sequence that captures the relationships between words like cat and mat. This encoded representation is then passed on to the decoder. The decoder then uses these encoded representations to predict the next word in a sequence. When it comes to predicting these words, the decoder is constantly referring back to the encoded input and predicting each word based on what has already been generated. And with that, it only generates words sequentially, one at a time. So, what can we learn from all of this? Today, we've explored how language models predict words, how word embeddings represent meaning, and the difference between static and contextual embeddings. By converting words into numerical values, adding positional embeddings, and then tokenizing these words, the model gives itself the ability to read, which enables the ability to understand context. The understanding of the relationship between word and text gives the model the ability to predict the next word, enabling it to write complete and coherent sentences.